Good afternoon, dear listeners. We continue our study for the theory of transmission line with distributed parameters. Today we will become acquainted with a very interesting mode of operation called the match load mode. This lecture will not be too long. As you can see, we have only 7 slides ahead. However, unlike the previous lecture, it will be much more mathematically intensive. Therefore, for you to understand this lecture, I recommend pausing this video and carefully examining how each mathematical expression is derived. Feel free to revisit any unclear moments as you progress through this topic. It will aid you in our understanding of the subject. And before this lecture, I ask you to subscribe to our channel so as not to miss the release of new lectures. Put likes. It will help spread knowledge among the maximum number of listeners. So let's begin our lecture. As always, let's start by recalling the previous lecture. In the previous lecture, we learned that the most optimal way to control the asynchronous motor's rotation speed is to use frequency converts. One of the main problems with variable frequency drives is the problem of long cables, which is the distortion of the voltage waveform at the motor terminals about the form at the terminals of the frequency converter. The traditional way is to solve this problem is used to sine filters. The previous lecture shows another way based on the knowledge of processes in non-distortion communication lines. We have proposed to use additional inductors to make the communication line between the frequency converter and the motor a non-distortion line. This method is more efficient and more economical. In previous lecture, I promised you that we would soon start studying other important and other interesting modes of operation of transmission line with distributed parameters. One such mode will be covered in this lecture. The mode we are going to study is called the matched load mode. In the matched load mode, the loading impedance of the line ZLD is equal to its wave impedance ZW. Let's examine in detail what happens when these impedances are equal. As we remember from previous lectures, and I hope you do remember, the voltage and current at any point of the line located at distance x from its beginning are described by these equations. This equation for voltage and this for current. The complex number A1 and A2 is these equations represent constant integration. If we will know the voltage and current at the end of the line, U2 and I2, the integration constants can be determined using the following formulas. This formula describes constant A1 and this for constant A2. Now let's recall lecture number 7, one of the slides which is shown here. You can follow the link in this QR code to view this lecture. In lecture 7, we introduced the concept of direct and reverse waves of voltage and current in the line. We also discussed that the integration constant A1 determines the amplitude and phase of the reverse wave. Let's examine this integration constant in more detail for the case of matched load. The integration constant A1 is determined by this formula. Let's divide this formula numerator and denominator by the same complex current I2. The fraction will remain unchanged. In the numerator here, we have the ratio of the complex voltage to the complex current at the end of the line. But this is precisely the complex impedance of the load. Therefore, in the matched load mode, the numerator of this fraction is equal to 0. Consequently, the integration constant A1 is also 0. This means that there is no reverse wave in the matched load mode. This is the most important property of the matched load mode of the lines. It implies that only the direct wave exists of the line, which only the direct wave exists in this line, and which is entirely absorbed by the load. This is no reverse, no reflected wave. Therefore, in the matched load mode, the power transmission is more efficiently and efficiency coefficient is maximum. But that's not all the interesting phenomena in transmission lines with a matched load. Let's see how the basic equations for a line with matched load are simplified. First of all, let's start with the equations for the general case. As we already know, and I hope you all know too, if the voltage and current at the end of the line are known, then at any point along the line at the distance y from its end, the voltage and current can be calculated as shown in these formulas. In the case of matched load, the wave impedance of the line and its load impedance are the same. Therefore, we replace the wave impedance with the load impedance in these equations. And let's consider that the product of the load impedance and the load current is nothing but the voltage across the load denoted as U2. Taking this into account, the basic equations can be rewritten as shown here. Note that the sum of hyperbolic sine and hyperbolic cosine of the product of gamma and y is simply equal to the exponential of this product. Therefore, for the case of matched load, the equations for finding the voltage and current at any point along the line take a very simple form, as shown here. Note that the voltage at any point along the line, in the case of matched load, depends only on the voltage at its end and the distance from the end of the line. And the current depends only on the current and its end and this distance. Furthermore, the proportionality coefficient between this voltage and current quantities is the wave impedance of line. This aligns very well with what we know from previous lectures. The wave impedance, as we have determined earlier, is the proportionality coefficient between the complex voltage and complex current for the direct and for the reverse waves. And since in our case there is no reverse wave and wave impedance is the proportionality coefficient between the total wave and total current at any point along the line. Now let's talk about another interesting aspect related to the input impedance of a line in a matched load mode. But let's start, as always, with a general case. Let's consider a line with distributed parameters with a known length L loaded with a known load impedance ZLD. Let's find the input impedance of our line. We will begin with the same equations we introduced in the previous slide. As we have mentioned before, these equations allow us to calculate the voltage and current at any point on the line located at a distance y from its end. In this case, the known values are the voltage U2 and current I2 at the end of the line. Let's mentally move to a distance from L from the end of the line, which is entire length of this line. If y is equal to L, then we are moving to the beginning of the line, and these equations describe the voltage U1 and current I1 at this point, at the beginning of the line. Now, please pay attention. The input impedance of the line, which is what we are looking for, is the ratio of the voltage at the beginning of the line to the current at this point. Therefore, let's take the ratio of the first equation, this equation here, to the second equation. This fraction remains unchanged if both the numerator and denominator are divided by the same complex current I1. Taking into account that the ratio of the complex U2 to the complex I2 is none other than the known load impedance at the end of the line. As a result, we obtain the following equation for finding the input impedance of the line. This is a general equation that is valid for any mode of operation of our line. Let's see how it changes in the case of a matched load mode. In the matched load mode, everything is greatly simplified. We take into account in the formula that was obtained earlier that the wave impedance and load resistance, load impedance, are one and the same. And as a result, we get that in the matched load mode, the input impedance of the line is equal to the impedance that is connected to at its end. And there is a load impedance. Or we can say that in the mode of a matched load, the input impedance of a line is equal to its wave impedance. This, in general, was to be expected. After all, a little earlier, on slide number 4, look at this slide, we learned that at any point of the line, or everywhere in the line, as we wrote earlier, the proportionality factor between current and voltage is the wave impedance. This statement is also true for the beginning of the line, that is, for the input current and input voltage. Our short lecture has come to an end. In it, we got acquainted with one particular case of the line operation, which the matched load mode. In this mode, the load impedance of the line is equal to its wave impedance. In this case, there are no reflected current and reflected voltage waves in the line. I take into account reverse current and reverse voltage. So all the electromagnetic energy propagating in the line enters to the load. In the matched load mode, the current at any point of the line depends only on the current of its beginning. The same can be said about the voltage at any point on the line. In this mode, and only in this mode, the ratio of voltage to current at any point of the line is equal to its wave impedance. In the matched load mode, the input impedance of the line is equal to the impedance of its load, or the wave impedance of this line. Depending on the ratio of primary parameters, other special modes are possible in which the line can operate. These modes will be discussed in detail in our following lectures. Be sure to subscribe to our channel so you don't miss the next lectures. Thank you for your attention. I wish you success in studying the theory of electrical engineering. Bye.